The question here is, why do we even need to use stress in design, not force or moment? Let's briefly review what we currently do in designing a structure or a structural element. Supposing, say, your structure has a couple of different materials involved in it, like steel, wood, aluminum, what have you, right? You list all that, then go and find their strength. Unless it's a new material, you're likely to find their strength either in a design code, book, or a catalog, right? Well, what is strength and how did they find it? Well, you find the strength through material testing in a laboratory. Well, there are what are called material testing machines, which allow you to take a specimen of material like this one right here and apply either a tensile force or a compressive force gradually until failure. Supposing, say, we used a small cylindrical specimen like this and applied a tensile force F. And of course, these days, material testing machines are fully computerized. So as you keep increasing F from 0, the computer is going to keep track of the value of F and the corresponding elongation of the specimen. All right. For each of the force value and the elongation value or the displacement value delta, you calculate a stress, which obviously is the axial stress, right, in that specimen, and the corresponding strain. All right, so stress is simply force divided by the initial cross-sectional area of the specimen A naught, and the strain is simply the displacement delta divided by the initial length of the specimen. Now you keep plotting a relationship between sigma and epsilon, and typically you will get something like this. The exact shape of the curve depends on the material, and the detailed discussion of that is beyond the scope here. But the shape here is sufficient for the purpose of the discussion here. The key here is that sigma, the stress, will keep increasing up to a certain point, at which point the strain will become unlimited with no virtual increase in the stress. In other words, you won't be able to increase the stress any more at this point. The stress at this point is what is called the failure stress or a strength of the material, right? And in this particular example, we applied a tensile force, and therefore this will be the tensile strength of the material. So this is how they found the strength for various materials. The second step would be to calculate the maximum values of the stresses in the structural elements. I have listed two different examples here. The first one is a cable system and the second one is a beam. We learned how to analyze this type of structures in statics, right? In the first example here, we'll go ahead and find the tensions in these cables, FAB, FBC, and FBD. We'll take these tensions and divide each by the corresponding cross-sectional areas of the cables in order to calculate the corresponding axial stresses in the respective cables. And similarly in the beam problem, let's say I take a cross-section at point A. I'm going to see a shear force and a bending moment, right? In this course, later on, we'll learn how to calculate the corresponding stresses due to each of these internal forces. We will learn that the bending moment will produce a normal stress sigma xx, and the shear force B will produce a shear stress tau xy. Here's a little differential element taken at a point like that, showing how these stresses act on that differential element. We will then consider various points on the cross-section itself and various cross-sections along the length of the beam in order to calculate the maximum value of sigma xx and tau xy for the whole beam. The final step of the design process would be to see if the stresses we have calculated are sufficiently small to be safe. To do that, this is what we do. Now remember, the material testing gives you the failure stress, right? But to account for all kinds of uncertainties that you normally have, what we do is we define what we call allowable stress by reducing the failure stress by a factor called the factor of safety. For example, in example 1, the allowable stress of this member right here, AB, would be the failure stress of that member divided by a factor of safety. So typically, factor of safety might be, let's say, 2, or maybe 1.5, maybe 2.5, something along those lines. Say cable AB is a steel cable, then you will take the failure strength of the steel, divide that by a factor of safety to calculate the allowable stress for steel, right? And similarly, let's say this is just a rope, then you will take the failure strength of the rope, divide that by a factor of safety. Now you take the stresses you have calculated for these members and see if they are smaller than the allowable stresses for these structural members. The approach is the same over here. We take the maximum normal stress that we have calculated for the whole beam and see if that is smaller than the allowable tensile strength of the material. And similarly, you take the maximum shear stress, tau xy, we have calculated the whole beam, and see if that is smaller than the allowable shear stress for the material. Now we can try to answer the question of why we use stress, not force or moment. Supposing, say, you tested 2 specimens of a material. The first one had a cross-sectional area of 1 inch squared, and the other one had a cross-sectional area of 2 inch squared. If you plotted force versus the displacement, you'll end up seeing 2 different curves. So the failure value of the force for this specimen is 100 kip, whereas the failure value of the force for this specimen is 200 kip. The reason is, the thicker the specimen, the stronger the specimen. In other words, the failure force depends on not only the material type but also the cross-sectional area. On the other hand, if you calculated the stress and the strain like we normally do and plotted a relationship between the stress and the strain, you would find that the 2 curves would approximately coincide. There's of course always an experimental scatter, right? No 2 specimens are truly identical. So because of that, it's not going to be exactly the same, but they're going to be approximately the same. And you can infer that from the numbers that I have on this picture here, right? The failure stress over here is going to be 200 kip divided by 2 inch square, so it'll be 100 kips per square inch. Whereas here it'll be 100 over 1, which is 100 again, right? Now you can see in a way, theoretically, I didn't even have to test two different specimens, right? Because they coincide with each other. So what's the point in testing 2 of them? All I have to do is to test 1 specimen. I would have found the failure stress from that test. But of course, we always test more than 1 for the reason I stated a little earlier, experimental scatter, right? Let's say we have a truss structure with several members like this. Let's assume that each member has different value for the cross-sectional area, but made of the same material. Say this is the steel truss, each member is made of steel. Say member 1 has area A1 and the member force F1. Member 2 has area A2 and the member force F2. If we use the strength of steel in terms of stress, we only need 1 value for sigma allowable, right? And the stresses in all members can be checked against this 1 value. On the other hand, if the above check is done in terms of F failure, in other words, the failure value of the force instead of the stress, then each member with this correct cross-section must be tested, right? How would I know the failure value of the force in member number 1 unless I tested it, right, with that cross-section? And similarly, I would know the failure value of the force in member number 2 unless I tested it with that particular cross-section, A2. In other words, to do this failure check, you have to test as many specimens as the number of members in this truss. Obviously, this is very costly, so we don't do that. Furthermore, cross-sectional area of some of these members could be so large that it won't fit in the testing machine. So you can see the fundamental as well as the practical difficulties of using the force versus displacement relations instead of the stress versus strain relations in the failure analysis.